last speaker today is Andrea Bevilacqua. His talk title is K-deformed finite boost for a two-particle system.
Then for two particles, so we very briefly introduce what is a Hopf algebra and how it is related to the group. And finally, once we have defined those two particles, then we look at what happens concretely and we study a simple case. And after this, we will conclude with some questions for the future. Okay, motivation. So of course, this is more right now. So we have gravity and we also have quantum mechanics, but a general theory of nature should encompass both, of course. Of course, it's difficult to study any kind of theory which implies all of them. There are many technical and also non-technical issues and also issues not of a technical nature, but more maybe of a philosophical nature. So what to do? Of course, we can give up. Nobody here will be happy with this. So we can build a model very directly, but of course here you need to make some assumptions and then you have to justify them. The easiest way out, let's say, is to find a physical regime where one can build some potential effective theory of quantum gravity, regardless of what the microscopic details would be, and then say that one. So what I will present today is one such model, which is based on Krakow-Minkowski spacetime. This is basically some kind of effective flat spacetime limit of quantum gravity. Basically, you put Newton constant G to 0, the h bar to 0 while keeping the ratio. This is just an intuitive description, of course, because all of these quantities are dimension 2, but it gives you an idea of the kind of regime we're in. And this kappa is intended to be some observer-independent quantities, basically just like C. Okay, so I will show you briefly how to go from the ground up, so from the very basics, and then up to some physical predictions. So how do single particles and antiparticles behave in this case? First of all, I will introduce what is the Krakow-Minkowski spacetime. Basically, the Krakow-Minkowski spacetime is a spacetime whose coordinates x0 and xi commute in this way. So this type of commutativity, of course, gives an algebra, and this algebra is called A-3 algebra. As I said, maybe I didn't say, but 1 over kappa as a dimension of length. This is clear also from this definition. And one usually assumes that 1 over kappa is of order of the Planck length. This is, of course, because, as I said, this is a kind of effective theory of quantum gravity theory, which means the kappa cannot be too small, the 1 over kappa cannot be too large. And the formal limit kappa to infinity is the classical limit because then this content is 0 and then. Okay, this is a very important definition, so how to build something on it. The first step is usually you take some explicit representation of this algebra. Here I wrote on one. And then you immediately go to the plane waves, which, by the way, plane waves means exponentiation, and this exponentiation is also the group related to this algebra. So, of course, a few things need to be said. We know that x0 and xi do not commute by definition. So here I could have chosen I must have chosen some kind of ordering of these exponentials. So I chose the one where the x0 is to the right and xi is to the left. This doesn't really change anything in our description. It's just a matter of choosing coordinates in momentum space. Well, in this way, formulas are really simple. And of course, this ki and k0, since both x0 and x are dimensional because of this 1 over kappa and from, then ki and k0 are dimensional too. And this can be repeated as momentum formula. So what do? We have these exponentials. Now we compute the exponential. This is just a definition. And whenever you do, you end up with this ek, which becomes this quantity. Now, of course, this P0, P, and P4 are some new coordinates which are usually introduced just for simplicity because in this way the matrix looks simpler. And I have this formula here. So one thing to notice is that although it maybe is not evident from this formula that I wrote here, but decay is completely determined once you know the last formula. So once you know P0, P and P4. And this is basically you can, okay, this is one thing to keep in mind. And moreover, if you take this vector, so 0, 0, 0, 0, k, and then you add it with the group element, you get P0, P and P4. Again, this is, it may seem so, it's amazing obvious, but it's important. And finally, which is the most important thing in this slide, so this P0, P and P4 are not independent, but they create this, they must satisfy this relation. This is of course a relation of the sector space. We can interpret this fact, if we interpret them as coordinate momentum space, we can interpret this fact by saying that momentum space is curved. As a matter of notation, this EK from the A and 3. Okay, so now we have basically plane waves. We have the group. How do we add momenta? Because up to now I just put some number to the connections. So of course, we cannot just add canonically the KA or the PA, which by the way are called Vickers product in classical basis. So what do we do? How do we sum momenta? So what we use is the group property. We can use the group property because, as I said, is EPA just from group. So whenever we multiply the group elements, we just get another group element whose momentum is the form sum of momenta. And you can do it with both bases. Either you can just write this either just in terms of this P or explicitly with respect to the K. And you get this to perform sum. Of course, here you have 5 of them instead of just 4, because here you need to use also this P4, but the surface is still 4-dimensional. The same thing, of course, happens for the -1. So what it means for a momentum to be minus something else, because usually you have a canonical minus, but here you introduce the minus with the antipole, with the inverse of the group. And of course, this antipole is such that a momentum, the form plus its antipole, in whatever order, is 0. Okay, so why use P and not K? Up until now, you can choose whatever you want, but here it's just easier to work with P, because basically you can just, instead of working with these matrices, which represent the position in space-time, you can switch them for canonical position in space-time, so T and X, by using a map. And if you use this P momentum. So we can work basically in a commutative space-time. Of course, commutative space-time doesn't mean that whatever object you build is commutative. For example, in this case, the Lie map of a single group element is just a plane wave. But the Lie map of a group product of two group elements is again a canonical plane waves, but whose momentum is the deformed sum, where this deformed sum is with respect to the classical basis. Of course, we may want to describe this, this is still a canonical plane wave just with a strange momentum. If we want to describe this in terms of products of two canonical plane waves, we can still do it, but the product is now not the canonical product, because otherwise here you would have a canonical plus. So you need to introduce this star product, which is in general non-commutative. Now, this is the very, very basics. So what do we do now? Basically, since the star product is not commutative, if we talk about complex scalar field, we have two possible actions. We have the S1 and S2, which differ for the position of the dagger, basically. These two are, of course, the same in the non-deformed context, because the star product reduces to the canonical product, and you can switch them off. But in our case, we just decide to use basically the average of these two actions. The 1/2 is over here, because in the limit kappa limiting, you need to recover the canonical. Now, here there are a lot of subtleties for doing the computations and then getting the neutral charges, but after a lot of computations, you can for example show that the translation to neutral charges are given by this. Now, this alpha p is present in all the charges, and it doesn't really matter for us. It's just something which is momentum dependent, and which goes to 1 in the limit kappa to infinity. So, for example, in this case, P0, you get that A like A is multiplied by minus antipole of omega, and you get a d dagger d by omega. So in the limit kappa to infinity, this is 1. This antipole is just another minus, so minus and minus plus plus, and you get the canonical charge. So everything works out from this point of view. But this is the same, the first sign if you want the particles and the particles behave differently. Basically, this A dagger is related to particles which contain an antipole in the momentum. And this B dagger, and B of course, is related to particles who don't have an antipole in the This is, of course, not ironclad, because the antipode of an antipode gives back the original momentum. But in any case, whenever you have a particle created with A dagger and a particle created with B dagger, you know that one of them will be the antipode of the other. So they will not be just equal and opposite. But notice that they have the same mass. This is, you can prove it easily. So how about boosts for single particles? Well, you can show basically the boosts for single particles behave exactly like in the non-deformed field. You can compute the boost charge, the vector charge, the boost vector charge from the action. You can compute all the charges, they satisfy the canonical Poincaré algebra. And basically the infinitesimal action of the boost on a single particle state is just dependent on the algebra. So you immediately get the canonical action. But of course, whenever you want to see what is the momentum of a particle or a B particle, although they are boosted in the same way, once you apply the operator here P1 because it is in the one direction, and P0, you get the particles created with A will have minus antipode of whatever. And particles created with B will not have this minus antipode. So for particles, single particles and single antiparticle, everything works fine. Basically, they have the same mass, but if one of them has momentum P, the other has momentum minus S of P, and of course these two are not the same. You can call them. They're not the same. So what happens when we have two particles? In particular, not when we have two particles, when we have what I mean is a two-particle state, because we can have two particles, but one particle one state, the other particle the other state. Here we want to see what happens when we have a tensor product of two states. And here we need to talk a little bit about the Hopf algebra, not related from the group. So I will not have the time also to go in detail about what is a Hopf algebra, but basically a Hopf algebra is an algebra, a coalgebra, and a manifold. So an algebra is an algebra, this is what you all know. For example, here the standard Poincaré algebra of the generators. This is just, if you pick some commutators, you compute, you pick some operators, you compute the commutators. A coalgebra is something which is a bit more complicated. Basically describes how these generators of the algebra act on tensor product of states. Of course, here I'm simplifying a lot. So there are some conditions that this operator needs to satisfy to have a consistent mathematical construction and also some inconsistencies. But this is what they do. So a coalgebra basically just describes how the operators act on the product of states. And we already met an antipode. This was the S. And basically it just encodes what it means to have a reverse transformation. So here we will only concentrate on the coproduct, because this is enough for us to obtain the boost for the first mistake. So in the non-deformed case, the coproduct is triggered. Why? Because if we have an operator here, let's use the translation operator just because. So and here we have a tensor product state. So it acts on using the Leibniz rule. So it is act on the first and act on the second, plus nothing on the first and act on the second. And then each of them here are eigenstates of mu. So you just get the total number. This is what is canonical. And of course, this can be described as a trivial coproduct acting on these tensor product states. For example, this one. And you see it here, you know? So this P mu atom P, this one atom Q, and then this one atom P, and this P mu atom Q. So this is very, very simple. So in the deformed context, the Leibniz rule does not work. So here I wrote down a very, very simple example of how to see it. So let's say we start with this object over here. Then since this, as I said, this is now a canonical frame wave, so everything works as usual. So this means that I can write this object here in this way, because this derivative brings down this momentum. And now this plane wave here, if you remember, I can write it using the coproduct. So this means this is a derivative acting on a coproduct. Now, if this derivative satisfies the Leibniz rule, then this must be true. So acts on the first and nothing on the second, and nothing on the first and acts on the second. But these, once again, these are just plane waves. So whenever I act with the derivative, I just put down items and momentum, and I get this. So if the derivative satisfies the Leibniz rule, then the deformed sum of momenta is equal to the canonical sum of momenta, and we know this is force. So this is just a very easy way to see that the mass not satisfy the Leibniz rule. So here I wrote down an example of the kind of rule they satisfy. So this is when a derivative with respect to 0 acts on a product of two things. And notice that I will not define what is delta plus, but it basically is something which divided by kappa goes to 1 in the limit kappa to infinity. So in the limit kappa to infinity, of course, you recover the action on the first and nothing on the second, plus nothing on the first and action on the second, and 0, because this is just close to. Now, here I got this down, and notice that this is very, very reminiscent of the formula for the sum of momenta, which I wrote down at the beginning. Here I write it down again, just to show this, the similarity. You know? This partial 0 of p is 0, and then this delta plus acting on the second thing of the kappa. This is the second momentum plus of the Capricorn. So this is basically exactly the same construction. This is of course just to give you an idea. You can prove this more mathematically, but we're not really here. So basically the action of the coproduct can be like this, and the coproduct, which describes how this derivative acts on a product state, is somehow related to the momentum group structure. I will not go too much into detail, but you can see it from here immediately. So, we are interested basically in the boost and rotation case because we will, this is what we need to understand. So basically we know that our manifold is AM3 and we want to add with SO13 on it. What to do? The easiest thing is basically to notice that both AM3 and SO3 are subgroup of SO14. So you go in SO14 and try to work there. And now in SO14 you use the so-called Iwasawa decomposition, which just means basically you pick this algebra and you split it into the SO13 and then the A and N, where A is generated by our time coordinate, if you want, the one at the beginning, and this N by the position coordinate. So basically this means that whenever we have some, here I wrote G, I should have wrote it in a different letter, but whenever we have an element of S14, and basically this given Kg and G, then there must exist two unique K prime G and G prime such that this relation holds. This must be true because of the Iwasawa decomposition. And if you multiply by the inverse, you get this object right here. And you see, this is basically the boosted group element, which will contain the boosted coordinates. And this is the canonical, the initial group element. This is the canonical boost, and this is something else which we will now explain. So usually to get the coproduct, we are only interested in infinitesimal transformation. So what do? Here, just to show the procedure, we use the canonical boost first, and then this K prime G is something which is kind of like the canonical, but with this added momentum-dependent matrix, which is the one which is responsible for all the non-trivialities in the coproducts. And you basically just pick this version over here, plug all the matrices. So this is G, this is G prime, and just the prime. This is Kg, and this is just K prime G. You just multiply, you equate times by times in the matrix, and you get the coproduct at the end. So here I'm not interested in the coproduct, but what I'm interested in is just in the boost. So what does it mean? It basically means do the same, but just with finite matrices. So here this is a finite boost. This is some matrix, which I know, but with all 0 here and a 1 here. And G prime had been defined before. Now notice here, of course, I'm talking about the boost of a single particle. But how can I get the boost of a two-particle space in this way? Well, basically the answer is to look at the boost, but of a product of group elements. And whenever you do, you get Kg times G. This is 1, and you can add them additive by N. And then this is additional matrix here. So what about this K prime GH? Because as we saw before, you can work out what this K prime G is, just with this. You can put this, we know, this is just technical stuff. But it seems as though, I mean, whenever we try to boost the particles, we still need something else. Luckily for us, it is completely relevant. Why is it relevant? Basically because this is once again our group element. And notice that basically the coordinates are in the last row. And this is just the definition. And this K prime G, whatever it is, I don't care here, but you have 0 here, 1 here, and 0 here. So whenever you multiply from the right with K prime G on a group element, doesn't matter which one, the coordinates are not affected. So I don't care what happens for the boost. So from this formula, which is the formula which boosts two things over here, basically the action of this acting on the right of G and of this acting on the right of H is completely relevant. So this means that we can define the finite action of a boost on a tensor product of states with momenta G and H as LG acting on G, and this is easy, so LG is the canonical boost, G is just a momentum. And then on H, just L prime G, which we know how to compute, because as I said, you just do this and plug the matrix in, and then compute the coefficient by coefficient. So now we know how to compute the finite boost for two particles. We just need to find this L prime G. So here, for simplicity, I will just expand at leading order in 1 over kappa. And whenever you do the computation, you see that this is the matrix that comes out. Of course, it's momentum dependent. And of course, this L prime G in the limit kappa to infinity reduces back to a canonical boost. And this L prime G, of course, we know already that it must be a boost, but you can check also explicitly that it satisfies the defined relation. So we now have defined two particle boosts, because we have L, we have the G, we have L prime G. So now see what happens. Basically, to see what happens, we study the phenomenological consequences by studying a particle and the particle pair, first in the center of mass frame, and then we boost and see what happens. And this will be the main result of this investigation, also quite interesting, I would say. So what happens in the center of mass? So in the center of mass, we do a leading order in 1 over kappa just to be relatively easy. So this deformed sum reduces to the canonical sum plus this term. And this deformed sum reduces once again to the canonical sum plus this term. So of course we need to impose that the total energy of the two decaying particles is equal to the rest mass of the decaying particle. And of course the sum of momentum must be zero. From this, we know that Pi and Ui are still not equal and opposite, but at least directed along the same line. So we can just move our reference frame somehow and just, for example, choose this mu and mu. This is not necessary, just to simplify things. And once again, you do this, you just solve them, and you get this result here. Of course, you can. I call this Q and this T, but you can just call them unsorted. And notice, of course, that in the capital infinity limit, this term goes away, and they are equal opposite, of course. This is fine. So this is basically what amounts, this difference amounts to the fact that one of them is the antipode of the other, you know? So this is what I wrote down at the beginning. So now we boost. How do we boost the particles? Well, here I just boost in the x direction. Here it doesn't really matter, but you can basically choose spherical coordinates where the z-axis is your x-axis where you are boosting, just for simplicity. Now we have two possibilities, either this tensor product or this tensor product. So in other words, either the canonical boost acts on P and the deformed on Q, or vice versa. So here I consider just the first one, because the other one you can just get by switching to Q. And here are the results. So this is, of course, what we expect. What is this picture here? So here I need to expect a bit. So basically, this is the distribution of momenta in momentum space. So of course, in the center of mass, the distribution is uniform. So you expect a particle to behave with equal probability in all directions. And the fact that this is a sphere means the modulus of the momentum is the same in whatever direction. Here I just there are three concentric spheres, and I just cut them up just to show you what happens inside. Otherwise, you will only see the blue outer shell. But there is a blue sphere here, which corresponds to the deformed cube. Then there is a green sphere, which corresponds to the deformed P. And here I added a red sphere, which is what happens for non-deformed cube. Remember that this P and Q have this additional m over 8k and 3m over 8k, which makes them in absolute value bigger than non-deformed. So the very interesting thing is now, by the way, to do this plot, I used a very non-realistic value of kappa, because it said this is expected to be of the order, 1 over kappa is expected to be of the order of Planck length. This is surely not the case, but this is just to highlight what happens qualitatively. These are interesting things what happens when you boost. So whenever you boost, of course, the momenta in the direction perpendicular of the boost have the same modulus. Momenta in the direction of the boost are highly modified, depending on the boost. now we see that so the red one, once again, is the shell of canonical momentum. The green one is the boosted P. So the boosted P, if you remember, is boosted with the canonical boost. So this slight difference is only due to the difference in the modulus of P. But the striking part is this. So this is the shell of Q, which is the second particle in the boost. So as long as you have your particle is the second in the tensor product for our symmetries, it gets completely different deformation. So it's strikingly different from this. Of course, once again, here I chose this very unrealistic value of kappa. If you choose a more realistic value of kappa, these are basically the same shell. You cannot really distinguish them by eye. Nevertheless, it's quite interesting, the difference from a qualitative point of view. And particularly, it is important to stress that here I'm considering only the first, here. As I said, I'm considering P and L acting on P and L prime acting on Q. You can say what happens when you switch them, because P and Q are not the same. You know? But the difference is very, very slight, even with these parameters which I use to exaggerate the difference. Basically, you get the same picture. So the important thing is that the deformed boost, finite deformed boost acting on the second particle is incredibly more, let's say, relevant than the deformation of the modulus sum. So I'll just conclude now. So, of course, the first obvious question is what are kind of the fragments in which this type of contribution to the deformation are more easily measured. And then the same thing, which is, in my opinion, even more relevant and more interesting than this. So here I wrote, of course, the boost for two particles. Now, and we saw that the particle boosted, which was second in the tensor product, was dramatically boosted in a different way. But now what happens if I have three particles? What happens if I have four particles, and so on? I mean, if I have 100 particle, is this effect high enough that the effect is, macroscopically visible, in which case this would mean something for this kappa deformed model? I mean, is the model wrong? Is the kappa deformation used to obtain the model wrong? This we don't know. Already, to get the boost for two particles was a huge amount of work. So I really don't know if there's some simplification for three or more particles, but this is quite a pressing question to answer this. So thank you very much.
Thank you very much for your talk. Are there any questions or comments? If not, let us thank the speaker once again.